Okay, so let's dive into this. You flagged some really interesting research about, well, the size of these large language models.
Right. They just keep getting bigger and bigger.
Exactly. It feels like every other week, billions more parameters. And you start to wonder, is it just about making them massive? Or are there like smarter ways to boost performance without needing uh, a supercomputer?
That really is the core question, isn't it? I mean, scaling up has worked wonders. Obviously, the AI capabilities are impressive.
Yeah, no doubt.
But the cost, the computation, the memory, it's becoming a huge bottleneck. It could really limit who can use these things, who can build on them.
Okay, so that's our mission for this deep dive then. We're looking at this research paper you found to see if there's a cleverer way, maybe a shortcut, to get more power from these models. Something beyond just adding more parameters.
Which you can kind of think of as like adding more connections in network, maybe.
Yeah, or more tools to a really complex toolkit. But adding tools makes the box heavier and maybe slower to find the right one.
That's a good analogy. And that's the traditional way, right?
Yeah.
Two main paths,
Hmm.
more parameters. So a bigger, more complex model.
Which needs more memory.
Exactly. And the other path is more inference time, letting the model sort of think longer, generate more tokens to work through a problem.
Which takes more time, obviously. So high costs either way, memory or time.
Precisely. And that's why this paper is interesting. It proposes a third way.
Ah, okay. This parallel scaling thing. Parse scale, they call it.
That's the one, parscale.
Mm.
The idea is instead of just bigger or longer, you increase the parallel computation, both during training and when you're actually using the models.
So doing more things at once, essentially.
You got it. And the really intriguing part is how efficient this seems to be at improving performance.
All right, let's get into the nuts and bolts then. How does parallel scaling actually work? What are they doing?
So the core mechanism is pretty fascinating. Imagine you feed an input, like a question, into the model. With parscale, instead of just one input, the system creates P, different versions of that input, using these special learned transformations.
P versions, like P for parallel.
Exactly. Then you take the same base language model, you don't need P, different models, and you run it P times simultaneously in parallel. Each run gets one of those slightly different inputs.
Huh. Okay, so P copies of the model running at the same time on tweaked inputs. Then what?
Then you get P different outputs. And here's the clever bit. They don't just pick the best one or average them. They dynamically combine them, aggregate them using a learned process into one final, hopefully better answer.
That sounds... It kind of reminds me of how those image generation models work, diffusion models.
That's a great connection.
Like they run things multiple times with slight variations using guidance, classifier-free guidance, CFG.
You're spot on. The researchers actually mentioned CFG as inspiration. The hypothesis is that CFG works because it does that double computation. Parscale basically takes that idea and says, well, why stop at 2? Let's try P parallel streams.
Right, scale it up. So how do they create these P different inputs? Just random changes?
No, not random. It's more controlled. They use a technique called prefix tuning.
Prefix tuning. Okay, what's that?
Think of it like this. You take your original input, and for each of the P parallel runs, you stick a short, unique sequence of tokens onto the front of it, a prefix.
Okay.
And the key thing is, these prefixes are learnable. The model learns during training what these prefixes should be to best guide the parallel computations in useful, diverse directions.
Ah, so the model itself learns how to create these slightly different perspectives. That's elegant. And then combining the P outputs, you said it was dynamic.
Yeah, dynamic aggregation. They use another small neural network. It's just a simple MLP, a multi-layer perceptron. Its job is to look at all P outputs and figure out the best way to blend them together, like calculating a weighted sum. It learns which outputs to trust more for the final answer.
And this MLP, this extra bit, how much does it add to the model size?
That's another efficiency win. It adds almost nothing. We're talking about maybe 0.2% extra parameters per parallel stream. It's tiny compared to the main model.
Wow. Okay, so just to recap, you get potentially big performance boosts by reusing the same model parameters multiple times in parallel, guided by these smart learned prefixes, and then combined intelligently by a tiny extra network, all without making the base model itself much bigger.
Exactly. That's the beauty of it. It recycles the model's existing capacity. It means you could potentially apply this parscale idea to almost any existing LLM, regardless of its architecture, training data, whatever task you want it for.
Okay, I think I get the how, but what about the why? Is there some theory behind this? Does it fit with how we understand model scaling?
Yes, absolutely. They didn't just build it and see if it worked. They developed a new scaling law.
A new scaling law, like building on the chinchilla laws?
Precisely. Chinchilla relates model size, parameters, and then data size to performance, usually measured by loss.
Right. Bigger models need more data, roughly speaking, to reach optimal performance.
So this new law incorporates parallel scaling. Their Proposition 1, Equation 4 in the paper shows how the loss, L, depends not just on parameters, but also on the number of parallel streams, P, and this crucial factor they call diversity, represented by rho.
Okay, diversity, that makes sense. You need the parallel runs to be doing something different for it to help.
Exactly. We don't need to get lost in the math, but the intuition is clear. More parallel streams, increasing P, should lower the loss, improve performance, if those streams are diverse enough, if rho is less than 1.
So what does the theory predict?
Two main things. First, if all the parallel runs just produce the exact same output, so zero diversity, rho equals 1, then the new law just simplifies back to the standard chinchilla law. No benefit from parallel scaling.
Makes perfect sense. If they're all identical, P1 is the same as P8.
Right. But second, if the predictions are different, rho 1, then increasing P does improve performance. If they're totally independent, rho, the loss improves with P following a power law. Diminishing returns, but still positive.
And what if they're, like, negatively correlated, rho less than 0?
Yeah, that's an intriguing possibility. The theory suggests that could boost performance even more. And that might be part of why CFG works so well in diffusion models, because it often uses a good prompt and a bad or negative prompt, which could create that kind of useful anti-correlation.
Huh. That's a really neat theoretical link. Okay, so the math looks promising. Did they test this out? What did the actual experiments show?
Oh, yeah. They went big on the experiments, large-scale pre-training. They used StackV2, that's a dataset heavy on code.
Okay, good for reasoning tasks.
And also the Pile, which is more general text. And they trained models up to 4.4 billion parameters, testing with up to P8 parallel streams.
And did the results match the theory?
They did, quite nicely. They were able to fit a practical version of their parallel scaling law to the experimental results. The equation they landed on, equation 5, basically shows that using P parallel streams gives a performance boost similar to scaling up the model parameters by a factor related to the logarithm of P. So O log P.
Log P. Okay, so the benefit of adding more streams starts to flatten out eventually, but the initial gains are pretty significant for a small P.
Exactly that. You get diminishing returns, but going from P1 to P2 or P2 to P4 gives you a nice bump, comparable to making the model noticeably bigger parameter-wise.
And did this hold up across both datasets?
Yep. They showed plots, figure 2, with the fitted curves for both StackV2 and Pile. The fit was really good, high R-squared values.
Nice.
And interestingly, the constant K in their fitted equation, which sort of measures how much benefit you get from parallel computation, was higher for the StackV2 dataset.
The coding one. Why is that important?
Well, it suggests that parallel scaling might be especially helpful for tasks that require more reasoning and complex problem solving, like coding, compared to tasks that might lean more on just memorizing facts, perhaps like some parts of the Pile.
Okay, so it potentially boosts reasoning abilities more. That's valuable.
Seems like it. And another finding from their analysis, figure 3, was that the bigger the base model, more parameters n, the more benefit you get from increasing the parallel computation. So large models gain even more from ParScale.
And they look beyond just the training loss, right? Did they check performance on actual tasks?
Absolutely. Tables 2 and 3 show results on downstream benchmarks, coding tasks, general language tasks. The pattern was consistent, increasing P, improved performance, pretty much across the board.
And again, maybe more improvement on coding.
Yeah, the trend was clearer there, reinforcing that reasoning aspect.
Okay, this is sounding really promising. Better performance, especially for reasoning, without just making the model huge. But what about the practical side? Like when you actually use the model for inference, what about memory and speed?
Crucial questions. And the results here are, I think, some of the most compelling. They specifically looked at memory usage and latency, how long it takes to get an answer. They argued, quite rightly, I think, that just looking at FLOPS isn't the whole story for LLMs because memory often becomes the real bottleneck.
Yeah, that makes sense. You can have tons of compute power, but if you're stuck waiting for data from memory.
Exactly. So memory first. Figure 4 in the paper shows ParScale adds only a very small amount of extra memory compared to achieving the same performance by just scaling up parameters.
How does that work? You're running P copies. Doesn't that take P times the memory?
Not quite, because the P copies share the vast majority of the weights. The main thing that increases with P is the size of the KV cache, that's the temporary storage used during generation. It does scale with P, but the KV cache is usually much smaller than the model parameters themselves.
Ah, okay, so the extra memory needed is manageable.
Very manageable. They found, for instance, scaling a 1.6 billion parameter model using ParScale with P8 needed up to 22 times less extra memory compared to just making the model bigger to get similar performance, especially at batch size 1, which is common for real-time use.
22 times less memory increase. Wow, that's huge for like running models on phones or edge devices.
Exactly. Low resource scenarios. And what about latency, speed? Does running P copies slow it down P times?
Yeah, you'd think it might.
Surprisingly, no, not really, especially at those small batch sizes. Figure 4 also shows latency. ParScale adds only a minimal latency increase. The reason seems to be that it shifts the bottleneck away from memory access towards parallel computation. And modern GPUs are really good at parallel computation.
So it keeps the GPU busy doing useful work instead of waiting.
Pretty much. For that same 1.6B model going to P8 at batch size 1, they saw up to 6 times less latency increase compared to parameter scaling for the same performance boost.
So way less memory, much less added latency. This sounds ideal for edge deployment. But wait, what about training? Running P copies during training sounds expensive.
That's a very fair point.
Huh.
Training P parallel streams could indeed multiply the computation needed.
So did they find a workaround?
They did. A clever two-stage training strategy. Stage 1. Do most of the pre-training the standard way, P1, on the bulk of the data. Get a good base model.
I would say standard stuff.
Stage 2. Then introduce ParScale training with P1, but only train for a shorter period on a much smaller amount of data. Just enough to learn the prefixes and the aggregation network and fine-tune the model for parallel processing.
So the expensive parallel part is only done on a small fraction of the data.
Exactly. Significantly reducing the overall training compute cost compared to doing ParScale from scratch on everything.
And does this two-stage approach actually work? Does the model adapt quickly in stage 2?
It's like it. Figure 5 shows the loss curve. There's a little bump when ParScale kicks in as the model adjusts, but then the loss continues to drop, showing it's learning effectively in that second stage.
And the final performance after two-stage training?
Still really good. Table 4 shows results for 1.8B models trained this way on 1 trillion tokens. Increasing P still gave consistent gains across general math and coding tasks. They highlighted a huge 34% relative jump on the GSM-8K math benchmark going to P8.
34% on math reasoning. That's substantial.
It really is. It underlines that reasoning benefit again.
And they didn't just train their own models, right? They tried applying this to an existing one.
Yeah, they took Qwen 2.5, which is already a very capable model trained on tons of data, like 1.8 trillion tokens.
Okay.
And even with that model, they showed that continuing pre-training using ParScale still improved performance on Pile and Stack V2. So even state-of-the-art models might benefit.
Wow. And what about fine-tuning? Could you add ParScale without retraining the whole base model?
Yes. This was another cool result. They tried parameter-efficient fine-tuning, PFT. Basically, they froze the original Qwen weights and only trained the new ParScale bits, the prefixes and the aggregation MLP. And it still significantly boosted performance, particularly on code generation tasks, as shown in Figure 6.
That's really interesting because it leads to this idea they mentioned, dynamic parallel scaling.
Exactly. If you can get benefits just by training the small extra ParScale parts, it means you could have one base model deployed. Then, depending on the need, you could choose to run it with P1 for speed, or P4 or P8 for higher quality or harder problems, all without changing the core model weights.
So you adjust P on the fly at inference time. That offers amazing flexibility, high throughput when you need it, high capability when you need that, from the same base model.
Precisely. Adaptability and efficiency combined.
This feels like a really different way of thinking compared to just chasing more parameters. How does ParScale fit in with, other related research?
Good question. The paper positions it relative to a few areas. One is other inference time scaling methods. Some techniques try to improve reasoning by making the model compute for longer, serially like generating chains of thought.
Right, step-by-step reasoning?
Yeah, but that increases latency and can sometimes lead to the model kind of going off track or overthinking. ParScale is different because it's about parallel computation, different trade-offs.
Okay, what else?
Classify-free guidance, which we mentioned. ParScale is like a learned, scalable version of that. Instead of fixed rules for guidance, it learns the transformations, prefixes, and the combination, aggregation.
Makes sense. More flexible.
And it also relates to model ensembling, where you combine outputs from multiple different models. ParScale is like an ensemble, but where the models, the parallel streams, share almost all their parameters. That's where the efficiency comes from.
So it's like a very parameter-efficient form of ensembling.
You can think of it that way, yeah. And fundamentally, they argue their parallel scaling law is a generalization of existing scaling laws, like Chinchilla, because it adds this new dimension of parallel computation.
It really does feel like it opens up new possibilities. What are the big open questions now? Where does the research go from here?
Well, there are quite a few interesting paths. One is finding that sweet spot
Mm,
for a given inference budget, memory latency. What's the optimal mix of model parameters, n versus parallel streams, p?
right. The best trade-off.
Also, more theoretical work on that diversity factor, or what really drives diversity. How does it scale with p? Are there limits?
Understanding the secret sauce of the parallel streams.
Exactly. And practically optimizing that two-stage training.
Hmm.
When exactly is the best time to switch to parse scale training? Can it be combined effectively with other techniques like mixture of experts, OE?
MoE also uses parallelism, but in a different way, activating different experts. Combining them could be powerful.
Potentially, yeah. And could parse scale be useful beyond language, maybe in computer vision or science? That's another open avenue.
So, lots to explore. But the main takeaway seems clear. Scaling up parallel computation is a really promising direction. It's efficient, boosts reasoning, works well in low-resource settings.
Absolutely. It's a compelling alternative, or maybe a complement, to just building ever larger monolithic models. It suggests smarter computation can be as powerful as just more computation.
It definitely gives us something to think about. You know, as AI gets built into more everyday devices, phones, cars, appliances, how will techniques like this, focused on efficiency and edge deployment, actually change how accessible and powerful AI feels in our daily lives? It's a fascinating thought.
It really is. The potential for more capable AI in more places is significant.
Well, this has been a fantastic deep dive. Thanks for walking through this research with me. It's genuinely exciting to see these new approaches emerging.
My pleasure. It's definitely thought-provoking work.
So just to wrap up the key takeaways for you listening, we looked at parallel scaling, or parse scale, as this third way to improve LLMs beyond just more parameters or more inference time.
We're using parallel computation guided by learned prefixes and dynamic aggregation.
We touched on the new scaling law that incorporates this parallelism and the idea of diversity between the parallel computations.
And the practical results showing significant boosts, especially for reasoning tasks like coding and math.
Plus, those really impressive efficiency gains much less memory, minimal added latency, making it great for edge devices.
Don't forget the two-stage training to make it more affordable to train.
Oh, yeah, crucial point. And that cool idea of dynamic scaling, adjusting P at inference time for flexibility.
And as we mentioned, for anyone who wants to really dig in, the code and model checkpoints are out there.
Definitely worth checking out if you're inclined. We'd love to hear your thoughts on this too. Does this change how you think about the future of LLMs? Let us know. It certainly feels like a significant step towards more efficient and perhaps more accessible AI.